The tail end of this is, and she calls it reaction yield. I call it percent yield. It's just when you're talking about stoichiometry, and let's remember what stoichiometry is because that's going to be on your test. Stoichiometry, remember, is the calculation of quantities in chemistry. So what we just did, and I spent a long time on that was the longest video to date. When you calculate how much, based on your math in chemistry, based on your chemical reaction, your balanced chemical equation, how much product you should be able to produce, that's called your theoretical yield. Back to my pancake example. Or you could do the same thing with cookies if you bake cookies, or if you're in industry and you're making a car part or whatever. If you have all the pieces, how much of this product should you be able to produce if everything goes perfectly? That is your theoretical yield. And on the back of a Toll House cookie bag, it says you need so much vanilla, so much flour, you need sugar, you need butter, you need all the components. And again, at least at my home, it would probably be either the butter or the eggs that you're going to run out of. And then it tells you your yield on the back, that you should be able to make 5 dozen cookies with that particular recipe. Well, that's if everything turns out just right. That's if you don't have someone that comes and snitches the cookie dough. That's if you don't make your cookies too large, or if you don't make them too small, or something doesn't happen and you drop some of the dough. If things turn out right, then you should be able to make 5 dozen cookies. That's the theoretical yield. So I hope I didn't overdo that. Okay, now based in chemistry, your theoretical yield is based on your limiting reagent, that reagent that's going to get completely used up in the reaction. Now sometimes that limiting reagent, you can have the perfect amount of each reagent, and yet as the reaction is happening, everything doesn't go as planned, and maybe the molecules aren't turned just right, and a lot of things can happen, and so maybe carbon monoxide forms instead of carbon dioxide. Things like that can happen, and so theoretical yield is the maximum amount that can form. All right, so then when you actually go into the lab and carry out the reaction, or the reaction takes place in nature, and what actually does form when the reaction takes place is called the actual yield. Then you get your percent yield. And your percent yield, you're going to have to do this in some of your labs. Your percent yield is your actual yield over your theoretical yield. And then to turn it into a percent, you multiply that by 100. Now let's go over it again. Your actual over your theoretical, what the math says you should get. When our cookie example, those 5 dozen cookies that the recipe says you should get. And then your actual yield, how many cookies were you actually able to bake? No snitching, no dropping, no whatever. Over the theoretical, that 5 dozen, then times 100. That would be your percent yield. And if you did a good job and you didn't have any snitching or errors, then you should get a fairly good percent yield. We're going to work an example problem. Here's acetyl salicylic acid. That is the chemical name for aspirin, acetyl salicylic acid. It is produced by the reaction of salicylic acid and acetic anhydride. This is a very common lab for students in Chem 2 to do, is to make aspirin in the laboratory, reagent grade aspirin. And that is the equation that goes along with it. Salicylic acid, acetic anhydride forms acetyl salicylic acid, and then acetic acid, which in common lay terms is just vinegar. So in a certain synthesis, 104.8 grams and then 110.9 grams of acetic anhydride are combined. It asks you to calculate the percent yield if 105 grams of aspirin are actually produced. So this is going to be a long drawn out deal, because if you have 104.8 grams of salicylic acid, 110.9 grams of acetic anhydride are combined, you're going to have to find first which one is your limiting reagent. Which one are you going to run out of? So she gives you the molar masses for each thing involved there and determines for you the limiting reactant is the salicylic acid. So we're going to take our salicylic acid, and I'm not going to go through that because I've already gone through that very long process with you. So we are going to take our salicylic acid, and we're going to go through this process. Okay, the salicylic acid is the C7H6O3. So we're going to work through this. And by the way, this one is in your textbook, and it is on page 106. So we're going to do this one. And the balanced equation for this is given there. Okay, and it tells us that we have 104.8 grams, and it tells us right there that this one is our limiting reactant. So I'm going to put LR for limiting reactant of salicylic acid. And so that is C7H, that's a 7, H6O3. Okay, and our unknown, that's our given. Our unknown, it wants to know how much acetyl salicylic acid that we should be able, I'm just going to call it aspirin. How much aspirin should we be able to form? Okay, how many grams of aspirin? And the chemical formula for aspirin is C9H8O4. Maybe I'll write the chemical formula so you get used to C9H8O4. Okay? Now from the balanced equation, we need to be able to see that for every 1 mole of salicylic acid we use, she uses that funny looking equal sign, we need, or we can produce 1 mole of aspirin. Remember that this comes from the balanced equation, and you have to have your balanced equation. That must come first, and she uses a picture balanced equation there. You can see there's 1 molecule of salicylic acid, 1 molecule showing of acetic anhydride. So that is your balanced equation. Okay? Am I ready to solve? No, because I have moles here, and my given has grams. I have moles here for the aspirin, and my given has, my unknown has grams. So I'm not. So I need those molar masses that she was kind enough to give us. So I know that for every 1 mole of salicylic acid, the C7H6O3, there are, for this one, it was 136.7 grams. No, that's not true. 138.12. 130, I'm getting this right out of the book. 138.12 grams. And for every 1 mole of aspirin, there are 180.15 grams. And so now I'm ready to solve, and I'm going to solve by starting with my given. So I'm going to say 104.8 grams and for every 1 mole, there are 138.12 grams. So I've used this one, and then I've got moles of C7 on top, so I need moles of C7 on bottom. So I'm going to use this first one right here, using this one now. That's the one I'm using. I wish I hadn't done that. I hope you can see that, because that's the one I'm using. For every 1 mole, I can make 1 mole of the aspirin. Okay, and I'm still not quite done, because that gets me to moles of aspirin, but I don't need moles of aspirin, I need grams of aspirin. And for every 1 mole of aspirin, I'm going to put aspirin there, and I can make is 180.15 grams of aspirin. Okay, so again, I'm going to take my calculator, and I'm going to say 104.8 divided by 138.12, and then times 1 divided by 1 times 180.15, and I got 136.69, which rounds to, I'm only allowed 4 numbers, 136.7 grams of C 9H8O4. This is my theoretical yield. Okay, so what am I going to do with that theoretical yield? This is how much I should be able to make. And now in the problem, it told us how much we were actually able to make. The actual yield, it told us, was 105.6 grams. If you'll read through the problem, it told us calculate the percent yield of the reaction if 105.6 grams of aspirin are produced. So our actual yield was 105.6 grams. So to get our percent yield, I'm going to do this on the same screen. Our percent yield is then going to be, on the bottom is going to go our theoretical yield of 136.7 grams. And our actual yield goes on top. And our actual yield, according to the problem, that will have to be given to you, is going to be 105.6 grams. So our grams are going to cancel. And then to turn this to a percent, you multiply by 100. So you're simply going to say 105.6 divided by 136.7. Then you're going to multiply this by 100 to get your percent, 77.2%. So your percent yield is 77.2%. And you can see that in your text on page 106. All right? And that finishes this chapter. There is one more section from this chapter that she goes through in this chapter, but we're not going to do it for this chapter. We're going to use it as an introduction for chapter 4 instead. That's how we're going to cover it. And the types of chemical reactions, because it just fits better with chapter 4, I believe. So I really wish that you would go through on page 109, this checkpoint for limiting reactants, and also mostly it's very helpful to work problems. You need to work several problems on theoretical yield and percent yield because they're a big deal.